Let's take a squared x equals a lambda x equals lambda into ax, as lambda is a scalar. This is equal to ax equal to lambda x, right? So lambda squared x. This can be written as lambda squared x. Now, the eigenvalues and eigenvectors, are they same for a and a squared? Let us check if there is any relation between them. So this can be written as a squared x equals lambda squared x, right? A squared x equals lambda squared x. Okay, x is same here, x is same. Only difference is in eigenvalue. Eigenvalue has become lambda squared now. Earlier it was lambda. So this gives an interesting property. For the previous example, we wanted to find the eigenvalue of A. Then the eigenvalue was lambda. When the matrix was squared, lambda is also squared. Eigenvalue is squared, but still the eigenvector is same. So with the same eigenvector, we have different eigenvalue, and that too the square of the previous eigenvalue. Okay, so our lambda 1 was, let's see, our lambda 1 was 6 in the previous example. Now it will be lambda 1 squared equals 36. Okay, our lambda 2 was 2, and now it is lambda 2 squared equals 4. So in general, we can have this property: a raised to nx equals lambda raised to nx. That means this can be marked as sixth equation. For nth power, let's make a conclusion. If for nth power of the matrix A, it is a raised to n. So if you want to find the eigenvalue for a raised to n, then you can just find lambda raised to n. That is the eigenvalue, and x is the same. The eigenvector is the same. Now, for what eigenvalues are good for? Let's see. It is good for eigenvalues. Eigenvalues. It is good for things moving with time. Things moving with time. As I already told you, when we move on to power system stability, if we want to analyze the stability of voltage, then V is also a function of time. It can be a function of time. So V of t. If power angle is del, then it can be del of t. These variables are moving with time. These are dynamic variables. These are dynamic variables. And if we want to analyze the performance of the dynamic system, then we can use eigenvalue and eigenvector as means. Now, when we convert a to a squared to a cube to etc. a raised to n, what happens here is n is moving from 0 to 1 to 2 to etc. So this is actually like each time we are taking one more step with respect to time. So our operating point itself may change. In that case, lambda is multiplied with itself. So for n, when n moves from 1 to 2, lambda moves from lambda to lambda squared. When n is moving from 2 to 3, lambda squared is moving from lambda squared to lambda cube. So for performance, dynamic performance analysis, this is easy. This property is making things easy. Okay. Now, another property, if A is shifted by C multiplied with identity, C times identity, then what happens to the eigenvalue and eigenvector? So let us take, now the new matrix is A plus Ci. So Ax equal to lambda x will look like this. A plus Ci into x equals lambda x plus Cx, right? Lambda x plus Cx, because Ax equal to lambda x. A into x is lambda x. A into C no, C into I into X is Cx itself. Okay. Now this is equal to lambda plus C into X. So now what happened? Earlier the eigenvalue was lambda. Now the eigenvalue is lambda plus C. Right. When the matrix was shifted by C times identity, the eigenvalue is shifted by, eigenvalue is added with C. Okay. So this is another interesting property. So for changes in the system, we are able to find the eigenvalue and eigenvector easily by some properties. Okay, so shifting A by the multiples of identity and eigenvalues will go up by C. Okay, so one matrix A taking powers in the sense raised to n equal to 0, 1, 2, etc. taking powers, or adding with multiples of identity, or whatever, we keep the eigenvector as same. X is same, only changes with respect to lambda. Lambda will become lambda raised to n or lambda plus C. Okay, so that is what. Now let us see another property for a generic 2 by 2 matrix. We'll take a 2 by 2 matrix A, B, C, D. Okay. Now, how will you take A minus lambda I here? If this is A, then A minus lambda I, determinant of A minus lambda I will look like A minus lambda, B, C, and D minus lambda. Let's evaluate this. Let's simplify this. So this will become lambda squared minus A plus D into lambda plus AD minus BC. Now determinant of A minus lambda I equals 0. So this equation will become, this is equal to 0. This expression is equal to 0. Right. Determinant of A minus lambda I equal to 0. Now, what is the form of this? Let's see. Let's analyze this form. This can be written as some lambda minus A1 into lambda minus A2. Okay. Normally this will look like lambda squared minus A1 plus A2 into lambda. Right. So here A plus D is there. So this can be, maybe we can say that this is A and this is D or something. Okay. So basically these are constants K1 and K2. This expression can be written like this. So the solution will be, as this is a 2 by 2 matrix, the solution for eigenvalues will be lambda 1 and lambda 2. Okay, so if we write lambda minus lambda 1 into lambda minus lambda 2 equals 0, this could be simplified in this form, right? And the solutions will be lambda equal to lambda 1 and lambda equal to lambda 2, right? So these will be the eigenvalues. Now, how will you simplify this lambda minus lambda 1 into lambda minus lambda 2? These are the solutions. Solutions of this equation is lambda equals lambda 1 and lambda equals lambda 2. This can be simplified as lambda squared minus lambda into lambda 1 plus lambda 2 plus lambda 1 lambda 2 equals 0. Now let's compare these two equations. Our generic matrix is A, which is A, B, C, D, and when you evaluate determinant of A minus lambda I equals 0, you get this. Okay, when you compare these two equations, you get that A plus D is equal to lambda 1 plus lambda 2. And what is lambda 1 lambda 2? Lambda 1 lambda 2. Let's here. Lambda 1 lambda 2 equals AD minus BC. So this is another interesting property, because from the matrix itself we are getting the eigenvalues by the sum of the eigenvalue and product of the eigenvalue. Both we are getting from the matrix itself. A, B, C, D is the generic matrix. A plus D, just the sum of diagonal elements gives you the sum of eigenvalues, and the AD minus BC is giving you this is determinant, right? AD minus BC is determinant. This gives you the product of eigenvalues. So from here, from these two equations, you can evaluate the eigenvalues. Now the sum is known as the trace of the matrix. the sum lambda 1 minus plus lambda 2 is known as the trace of the matrix, and this is known as the product or determinant. Product or determinant. So this is also an interesting property. This is why we are using eigenvalue and eigenvectors, eigenvalues and eigenvectors and their properties to analyze the dynamic performance of the system. What's the relation between eigenvalue and stability? In general, mathematically, the differential equations, if they have solutions going to 0, that means that is we want y of t. If the differential equation is on y of t, or we are taking y dot of t. If it's a linear differential equation, we have already seen y1 dash of t and y2 dash of t. So our solution is y1 of t and y2 of t. These are time dependent variables or dynamic variables. Now for t tends to infinity, what should happen? It should go to 0. So the solution of the differential equation should go to 0 when t tends to infinity. T tends to infinity in the sense the effect of input is over. The effect of input is not there in the system now. That is what it settles down. Basically, it's steady state. What we mean is steady state. It's not t tends to infinity. T tends to infinity means mathematically t tends to infinity means steady state only. Okay. Now let's see. The solution comes from solution in the sense solution for the differential equation. We have already seen that it comes from e raised to lambda t into x, and we saw that the complete governance with respect to time, the dynamics is confined to this exponent, right? That is why lambda is so important. The sign of lambda is also very important, right? Now, if lambda is negative, then this is exponentially decaying. When lambda is positive, this is exponentially rising. Okay. Now, suppose if lambda 1 less than 0 and lambda 2 less than 0, we have two eigenvalues if it's a 2 by 2 matrix. So what will happen? In both the cases, this is declining, exponentially decaying or exponentially declining, right? So this can be one condition for stability, right? E raised to lambda t will tend to 0 when lambda 1 less than 0 and lambda 2 less than 0, right? Now, this is when lambda is a real number. If lambda is a real number and if it is 2 by 2 matrix, two eigenvalues will be there, two real eigenvalues will be there, lambda 1 and lambda 2. The condition for stability can be lambda 1 less than 0 and lambda 2 less than 0 because it will exponentially decay to 0. Okay. Now, sometimes we can have complex eigenvalues also. Then lambda will take the form a plus or minus j omega, right? If that is a form, then real part of lambda equal to a, it should be less than 0. This is the condition, right? This is condition for stability. Now, without finding the exact eigenvalues, we can say that trace is negative. Trace is negative. What is trace? What is meant by trace? Because now we have two eigenvalues, both are negative for stability, right? Both are negative for stability. Then this is product, right? Lambda 1 plus lambda 2. Trace is this one. Sum only, not product, sum. Okay, trace is sum. So if as both are negative, lambda 1 plus lambda 2, here, let's take 1 minute. Lambda 1 plus lambda 2, lambda 1 plus lambda 2, and both are negative. So trace is negative for stable system, right? Now what about product? Both are negative, right? Lambda 1 and lambda 2. So product will be positive. Product will be positive. Product will be positive. So product will be positive and trace will be negative if both eigenvalues are negative, and that is a condition for stability. So basically, this satisfies stability and positive product. This also satisfies stability. Okay. Now, if complex, then what about the product? Complex means lambda 1 is complex and lambda 2 is complex. Lambda 1, lambda 2 equals a squared plus omega squared. If it is in the form a plus j omega, then it will be in the form a squared plus omega squared, which is greater than 0. So sum is again, this is product, right? Sum is again greater than 0. So these are the conditions for stability. Conditions for stability with complex eigenvalues. Complex eigenvalues. These are the conditions for stability here. These are the conditions for stability for real eigenvalues. Real eigenvalues. So that's it with the eigenvalues. Now we can slowly move on to the introduction to power system stability. What is power system stability? What are the types of stability analysis in power system? What is meant by damping power? What is meant by synchronizing power? What is meant by damping torque? Equal criteria, voltage stability, then right eigenvalue, left eigenvalue, right eigenvector, left eigenvector, participation factor. A lot of concepts are there, but mostly these concepts need an elementary introduction to linear algebra. That's why the first lecture was given in this form. Okay, thank you.